This week we're going to cover multi-level modeling in the application of longitudinal data. Multi-level modeling can be used for many different things, but this week we're going to really focus on longitudinal, and we're going to compare it to latent growth curve modeling, which we did in last week's video. So if you haven't seen last week's video, it's a good primer for this. We're going to reference a lot of things that we talked about in last week's video. So we're going to use this data from Pat Curran. This is from 1997. I'm using this data because it's covered in the book Applied Longitudinal Data Analysis by Singer and Willett. And this is an outstanding book. It walks you through, they have all of these extra resources that walk you through how to do all of these analyses. So I'm just going to follow their example that's in the book. You can find the data on the UCLA website. I just Google ALDA longitudinal, and this is usually the link that comes up first, and you can find this data to actually run this data along with this presentation. In this sample, they were looking at adolescents. They were trying to find out if there was substance use behavior. So they have a few different variables. They're looking at the peers of the adolescents and also the parents of the adolescents. And they used the term alcoholic. This is probably not a preferred term, but just what they're using at that time. They've got 3 time points. They're measuring the kids at age 14, 15, and 16. So those are the key things we're going to look at in this data set. When we look at this data in multi-level modeling, we're going to use the long format. So last week when we showed repeated measures and then we showed latent growth curve modeling, we used the wide format. So the wide format, again, is just to remind you, each person has 1 row. The long format, each time point has 1 row. So we can see this person 1 is measured at age 14, 15, and 16. So it has 3 different rows for those 3 time points that this person is measured. Notice some other things about this data set where it's measured in gender in a binary format. So it's just got a male, and you're either not male or you are male, so it's a binary variable. Age 14, this one's an interesting variable. We talked a lot about this last week. This is when we center the data, and what we're doing is we just subtract 14 from the age. And what this gives us is that at age 14, it says that it's 0, age 15 it will be 1, and age 16 it will be 2. So we're going to actually use this age 14 variable in our analyses because it's centering it so that our intercept is at that first time point. If we left it at 14, 15, 16, it throws off all of our interpretation, makes it much more difficult to interpret. We got alcohol use at these different time points. So this is a time varying covariate. So this changes over time. We expect this is the outcome variable, so this does change over time, of course. And then we've got peer, which is how much peers use at age 14. So this is not a time varying covariate. This is just at that first time point, and we just carry it forward. We also have the child of alcoholic. This is the parent variable, how much, if the parent drinks or not. So these are centered too, so I won't go into detail about that, but sometimes we want to center those variables as well. All right, so one of the things that we'll do is we'll want to look at our data to see how well straight lines fit the data. So it's often best to look at figures of this. So this is only a few of the people. So in this, we're only going to look at this subset of people. So it makes it more manageable so we don't have a ton of figures to look at, but we might want to look at all of the people and just see how well it fits the data. SPSS is known for its ease of its drop-down menus, and this is making these graphs is not easy because of the long data file format. You can do it, but you have to fit a linear regression line to it. It makes it a little bit more complicated to do with the drop-down menu. I've got some other slides that I can add later to show this, but on how to do it with the drop-down menu. The other way to do it is just to do the syntax, and this is not really simple syntax. It's actually quite complicated, but what I do is I'll just take the syntax from my different analyses and just change the main variables that I'm interested in and just replace them. So you can find those variables here, and then I just replace it to whatever I'm looking at. So if we're looking at the data, we have some people, for this person here, number 32, this person, the line fits the data really, really well. Other people, we've got a little bit of a misfit with straight lines. So person 82, there's a bit of a gap between them and the line. So it's not a perfect fit for that person. So we could test out in our latent growth curve modeling, we talked about different types of nonlinear patterns that we could fit to the data. In here, I'm just looking at straight lines, but maybe we would want to look at some nonlinear growth for kids' alcohol use. All right, and then we can also break the data down by some of our outcome variable, or I'm sorry, our covariates. So this is the child of a parent who drinks alcohol, and yes or no. And so again, they use the term alcoholic, but I just think it's better to say parent who drinks alcohol. So these are the trajectories for kids who parents don't drink. These are the trajectories for kids who do drink. So we can look, do we see a difference here? It's a little bit hard to see anything with all of these different trajectories. People are going in many different directions. This is much more interesting data than I had last week with the intelligence testing. Maybe we have kids starting off a little higher for this. So we've got a lot more kids up in this upper range, and in this we have kids in a lower range. So maybe there's an intercept difference between these. We'll actually see when we look at the data, but this just kind of gives us, we can start looking to see if we see patterns in the data. Same things with peers, if peers drink a lot at age 14 or not a lot. So it's just a median split to make it, we took the median amount of drinks that the peers would drink, and then we just broke it in the middle. And this just makes it easier to graph, and also just a dichotomous variable is a little bit simpler to interpret. So for this situation, we'll use a dichotomous variable, but it could easily be kept continuous. Low peers, having peers that drink less are on this side, and having peers that drink more are over here. This we might see some effects. We probably see an intercept effect. Kids who have peers that drink more seem to be already starting off drinking more at age 14. So we'll see what happens when we do the analysis. All right, so these are the equations that I had formulas from last week. It's not all that different. We're going to start off the data analysis the same way we did last week. We're going to start off with the no growth model. So just we're basically saying everybody doesn't change, so the no change model. So what we've got here is where every individual is fit with this formula. So they've got an intercept, which is made for them uniquely. So it's got that I component, plus some error at each time point. So the J is the error at the each time point. We've got here, this breaks down the intercept term into different components. So we look at an average for everybody, plus some difference for that individual. So we've got two error terms in here that are actually interesting, and we talked about this last week, but this error term is the error for the individual at each time point. So when we had that trajectory, we had one person that had a bit of space between them and the line. So that's that error associated where they don't fit that trajectory. So here is that amount of error. This is that we'd like to fit this as best as possible. We want this number to be smaller. So that gets at how well we're fitting our line. So whether we have a straight line, a curved line, a growth curve, whatever it is, we want this number to be as small as possible, meaning we fit each individual's data the best with our trajectory. This is that component where we had a bunch of intercepts. Everybody started off at different time points, and that's the variation associated with that. So each person is a bit off of, if this super dark red line I'm drawing in the middle, everybody is a little bit off of that average intercept term. So that's that fudge factor for the individual, or the adjustment for each individual. All right. In Singer and Willett, they use this composite model where they just take all the different components and just simplify it into one equation. So you've got the average plus their adjustment for each individual plus their error associated with their curve. All right, let me clean up this slide a little bit. And these are just in there to kind of show that. So when we actually do the analysis, in SPSS, I'm using syntax. It's really simple syntax. So what I'm going to look at is alcohol use as my outcome measure, and I don't have any other covariates in here, and all I'm going to do is look at a fixed variable of an intercept. So we're going to have an intercept only model. So this is, and it uses maximum likelihood. So this is a rather simple model. Again, it's no growth, no change model, intercept only model. And so this is all that I have to type in to get the output. When I have the output, I have this is the output I get. I have this intercept, which is the average intercept. This is where everybody starts off on average. And then I've got these error components that I mentioned above. So I've got these two error components. So this is that within this 0.562 is that within person variance, and that's how well I'm not fitting the person with my straight line. So there's this number we hope will go down with the next model where I have a better change model. So here I have a no change model. There's a lot of error with me trying to fit a no change model to each person. So hopefully that number goes down. And then this number here, this last number, is my between person. This is the initial status. This is the difference where people start off. So again, this is where we see the data coming out of SPSS. This is my average. So on average, I've got 0.922. That's where I'm getting this term here is at 0.922, and then in my output, let me get everything on this slide. So my 0.922 comes from there in the SPS output. I've got my residual. This is the residual of what's left over in the person after I fit that line. So this is the 0.562. And then I've got my intercept. This is the variance around that intercept, the adjustment for each person's intercept. So that's this value here. I'll show this again in the latent growth curve model. We have these. To me, it's a little bit easier to see in this latent growth curve model. This here is my average intercept, or my average initial level. That's at 0.92. This is the variance around that initial level. Everybody has a different starting point. So this is that variance associated with that initial level. And then I've got here, this is the leftover. This is what doesn't fit for that person. So when I fit a person's line, oops, let me actually correct that line. This is a no growth model. When I fit that person's line, there's variation around that line that doesn't fit the person. So that's this term here. All right, when I do it, and just as a reminder, when I do this in latent growth curve modeling, this is the syntax. This is the very elaborate syntax. What we talked about last week was that the syntax could be much simpler. M+ actually calculates these things by itself. So the one part of syntax that I'm going to have is I'm going to create a factor. I'm going to call this a level. I could call it intercept. I could call it whatever I like, but I'm calling it level here. The intercept is indicated by alcohol use to alcohol use 16, so all of the alcohol use variables. And this dash, what it basically means is it's just shorthand. Use the variables from alcohol use 14 to 16. So if there's a bunch more in between, it just makes it's a little simpler, so you don't have to write out all the variable names. And then set all of these factor loadings to 1. So that gets me these ones, the factor loadings, to be 1 for this initial level. The other part of the syntax is not needed. M plus, when we do the latent growth curve model in M plus, we don't need this. M plus will automatically calculate a mean for this initial level. It will calculate a variance for this initial level. So this is gets at the variance for that. And here I've got a star, which means starting. That means estimating. I'm starting the value at 0.5, but you don't even have to put a number in there. Just again, you don't need any of this line. M plus will calculate that automatically. And then I'm setting these residuals here all to be equal to each other. So last week I had a just term in the parentheses, I said residual. Here I just have 1. It just means it's 1, here's one number you're going to calculate, and it's just labeled 1 in this example here. All right, and then here's my output. Again, this 0.92 is my intercept, my average intercept for everybody. I have a variance of my level. So this 0.564, that gets at the different starting points that people have. And then I have these all to be set to equal. That's where what I just mentioned in syntax was I'm setting these all to be equal. And that's the misfit for each person, how much the line is missing from fitting their data. So in this situation here, I've got a lot of misfit. So this I should improve with the next model. With our latent growth curve model, we'll also get fit indices, and we'll use the fit indices to see if the next model fits better. All right, and then just to show on the same, all in one slide, I get the same numbers that I did from SPSS. I get this 0.92, which is the average, the 0.562, which is the residual, and then my variance around that intercept is 0.564. So I can get the same data out of that system. All right, and then here is my second model that I'm going to fit. The first model was a no change model. This model is a linear change model, and this is the average linear change on top. Looks nice and pretty. When we actually chart out the data, we get these interesting patterns, and this is where I think we can say a lot more about our data when we look at these individuals. So these individuals up on top, they have that similar trajectory that the average does, but we also have people that are starting off drinking and then they go down over time. So we have a lot of crisscrossing in this figure. Not everybody is just growing. So there could be even more improvement to this linear growth pattern, but we'll have people with negative slopes and people with positive slopes in this. All right, so when we fit this using that composite formula, we've got an average intercept plus an average slope multiplied by time. And then we have these residuals. And so we've got a residual around that intercept. So everybody has their own starting point. We have a residual around the slope. So everybody gets their own slope. And then we have an error associated with not fitting that person properly. So let me walk through these in more detail as where these come from. So we've got, and let me get my red lines off of here because it throws off the slide. All right, so we fit an average trajectory where people are starting at 0.65 alcohol use, and then they're changing 0.27 at each time point. And again, what I've got here is a centered time. So on this figure, I have 14, 15, 16, but the way it was actually calculated, it was 0, 1, 2, so that this number makes more sense. If I had to take this out to 14, the number would be very different and not be as easy to interpret. All right, so let's look at these variance components. So we've got this first variance component. This is the, let me just put it like this. This first variance component, this is that misfit around that line. So again, this is how well or how not well we're fitting this line. So if I've got these data points here, this person is not exactly on the line, so there's some misfit to this line. Before, this number was 0.522, we've got it down to 0.337, so having that linear growth is better than having no growth at all, but we're still not fitting each individual as well. We can still explain more of this. Probably if we went to some sort of nonlinear model or something else, we could probably fit this data even better. We've got these other variances. This variance here is in initial status. So our average starts off at 0.62 and goes up. We have a lot of variation. Each person has their own intercept. So this is that adjustment. So this person here has an adjustment that goes up quite a bit. This number, this 0.624, gets at the variance, the whole variance associated with that, those adjustments. We also have a variance associated with the rate of change. So this 0.151. So on average, we had a growth starting here and going up. Some people have steeper growth. Some people have flat growth. And then we also have people with negative growth. So there's variation in the slopes. And this number here gets at the variation in the slopes. So I think that's interesting, as well as just how much people can go up and down. Each person has their own individual curve, which is great in this type of analysis. In repeated measures ANOVA, everybody would be fit to this one line. And then this covariance. This is, to me, probably the most interesting number that we get out of these analyses, one of the most interesting numbers. It's the relationship between where people start and how much they change. So if people start off higher, do they change more or less? If people start off lower, do they change more or less? And here we've got a negative number. So basically saying if people start off higher, they're actually changing probably less. They're not changing as much. This is not significant, but if this were significant, we could say if you start off with higher alcohol use, you're tending to not grow as much as people who start off with lower, which kind of makes some sense. If you start off with lower amounts, you've got more room to grow. You've got more room to drink, versus people who start off higher, they don't have as much room to change. But this is not significant in this example here. And then just to show this, in the latent growth curve model, I think it was easier last week when we talked about this. We've got the variance associated with initial level, so everybody gets their own starting point. The variance associated with slope, so everybody gets a different slope. We've got our means of these, so we have an average starting place and an average slope. And then we've got our covariance between our level and our slope. And this is that number that I was just mentioning. I'll clean this up a little bit. This number here, this is the relationship between where you start and how much you change. So this is, to me, again, a very fascinating number. Does where you start affect how much you change over time? And then we've got our misfit for each individual down here. So we've got our residual of misfit. So this person's line is misfit. So how much misfit do we have? All right, and then just a reminder what we have with our syntax in M+. So this is latent growth curve modeling is in M+, multi-level modeling is in SPSS. So we have our initial level, which we had previously. So that's everything is set to 1. And then our slope is what's new here. We've got our slope is indicated by alcohol use 14 at 0, alcohol use at 15 at 1, and alcohol use 16 at 2. So when we do latent growth curve modeling in M+, we don't have to center the data. We don't have to adjust that variable. What we'll do is just set this to 0, 1, 2, and that has the effect of centering the variable. In SPSS, we actually have to compute a new variable that is set to 0, 1, 2, 0 for 14, 1 for 15, 2 for 16. So there's a slight difference between the two techniques. In SPSS, you have to do an extra step of centering the data beforehand. Here, you just do it when you create the syntax. These other components, again, you wouldn't need to. It's going to calculate the average intercept and average slope. M+ doesn't need that. It just knows to do it. We're going to say other means to 0. This is just to kind of simplify the output a bit, so we don't calculate the means. M+, if you use the latent growth curve syntax, we'll do that already. And then also what else is new is this correlation between level and slope. So in this situation, I've got a star. I'm just saying M+, go ahead and calculate that. Again, M+ knows now to do that with, in newer versions, it knows to do that. Okay. And then when we get our results, these results are they're exactly the same as a result in SPSS. So we have a mean of each of these. So this is the mean of the intercept, the mean of the slope. We've got a relationship between these two, the covariance between level and slope. So that's there. We've got our variances associated with our starting point and variance associated with our slope. And then we have our leftover, how well we're fitting each individual with that straight line growth pattern. All right. And then just this shows that we get the same results as SPSS. Okay. So as we're building these models, when we first looked at the data, we had some other covariates that we could add to the model. So we had the children who had parents who drank, and then we had how much the peers drank at age 14. So in this situation, these are time in non-varying covariates. I think I could say that probably better, but basically things aren't changing over time. So we could look at peers drinking over time, and then we have a time varying covariate. We could put that into this model, but in this situation we just have how much they were drinking at age 14. So in these different examples, we have the first model, which just adds in, do the parents drink? And in this situation, it's a binary variable, yes or no. Do parents drink, and how much do peers drink? So we have this variable. And then this final model, I'm not even going to go over it. This is, they were trying to get the best fit in the Singer and Willett book. And peers drinking didn't affect the slope, so they took it out. And this gets you the best fit. But I think that, Model D kind of will tell us what fits, or what's a significant predictor and what's not. So Model D will give us enough. Okay. So the first model, just to see what we would add to M+, is this level regressed on child of alcoholic or parents who drank, and then the slope regressed on. So that gives us these new values, these new regression values. And so we can look at, does having a parent who drinks affect where you start, and does it affect how much you change? And then we have, and I don't know where the SPSS part went to this, but I had a SPSS, the SPSS syntax, but when we run the models, we get what we're interested in are these new variables, and so we can look at the regression. So here's 0.743. This is the effect of having parents who drink on where you start. And then here's the effect of having parents who drink on your slope. So we'll get this with SPSS as well. So we'll get a effect on the intercept and effect on the slope of that. All right, and then in Model D, it's also adding in the amount of how much your peers drink. So this has got the different models here. In the first model, we don't have peers drinking involved. In the next model, we actually have that, and we can see when we look at all of these in this Model D column, we've got an effect of your parents drinking on where you start. Clean up all of this real quick. So an effect of your parents drinking on where you start. Your parents drinking does not affect your rate of change. So if your parents drink, you don't tend to drink more or drink less. If your peers drink, or if they drink a lot, it affects your initial starting point, and it doesn't affect how much you change. So we can look at these variables and it seems to affect where people start, but it doesn't affect if they're changing more or less. So it's kind of an interesting analysis. Having these risk factors might get you started earlier, but it doesn't get you drinking a lot more over time or a lot less over time. But it just affects where you start or where the person starts. I forgot I had these fancy things in here. So we could simplify the model. We could take out these variables that are not significant, and that's what they did with Model E. We'll get a better fit with it if we take these values out that aren't significant. But if kind of looking at this, we already see that they're not significant. So I would almost stay with Model D and just show that, hey, this is not significant. We tested this rather than just aiming to get the best model fit. In this situation, it's kind of nice. We have this question: does having parents who drink or having peers that drink, does it affect how much you change? And we can say, no, it's not significant. All right. This is just sort of the diagram, the Model D with everything and having the peer values in here as well. So what we found was that neither of these are both non-significant. And so your peer drinking, I'm sorry, I did that incorrectly. The effect of peer is significant on where you start, but not on how much you change. So we can, by adding this in here, we found out this is not significant, but the initial level is significant. All right, and then just briefly show you, this is their Model E where they pull out this non-significant. This had, they're calling it close to significant, so they left it in there because they thought it added some information. So it's a p-value less than 0.1. So in order to avoid a type 2 error, they left it in there, but we could also remove that as well.